right, guys, welcome back. This is going to be our last section in Chapter 5, and we are going to continue learning about probability here in 5.3. Remember 5.1, we introed the section. We talked about different types of probability, and then in 5.2, we introed compound probability, and versus or problems, and we looked at probability tables. In 5.3, we're going to continue down that path looking at just different situations. As you've noticed before, these are very practical problems. So we're just going to kind of continue logicking through them, applying some supplemental definitions and stuff along the way. So let's start with this problem. Jacqueline, as a nursing major, is required to take a course in psych, one in anatomy and physiology, and she also wants to take Spanish 2 for her minor. If there are 4 sections of psych, 2 of anatomy and physiology, and 3 of Spanish, how many different schedules could Jacqueline choose? Okay, I want you to pause the video and try and figure this out. How many different schedules could she choose? Well, there are a couple different ways to look at this. For one, now that you've solved it, you might have come up with the answer. What I hope you came up with was 24 different schedules. Now, some of you probably came up with this number by multiplying 2, 4, and 3, right? There are 4 sections of psych, 2 of anatomy and physiology, and 3 of Spanish. You've learned the multiplication rule in the past when it comes to probability. If I want to know all my different options, multiply all 3 of those together. 2 times 4 gives me 8. And if I multiply that by 3, I get 24. Okay? But another way of visualizing this is by creating a tree diagram. Okay? What's a tree diagram? Well, a tree diagram is going to look kind of like how it sounds. It's going to look like a tree. And what I'm going to do here is I'm going to make branches of my different options. Okay? So first things first, they tell me that Jacqueline is able to take 4 different sections of psychology. So I'm going to make 4 branches, 4 different sections of psychology. Okay? 4 different branches, okay, because there are 4 different psych classes offered. And then for each of those psych classes, she has 2 different options of anatomy and physiology. And then beyond those 2 options, for Spanish, there are 3 different options. So let's say she chooses the first section of psych, the first section of anatomy and physiology. Even if she does that, she's going to have 3 more options for Spanish. And when we finish making our tree diagram, if we sum the amount of bottom branches, you get the total amount of options in your sample space. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 different options. Now you might be sitting here and going, well, Mr. Carter, just multiplying them out is a lot quicker. Yeah, but the tree diagram provides you a nice visual. If I wanted to see all the different options in my sample space, okay? Maybe my best friend takes second section psych course. Well, then there are still 6 different schedules I can come up with to have a class with her or him. You get the idea. Okay, so a tree diagram is super useful for visualizing a sample space, and the end of the tree diagram will tell us how many options are in that sample space. So I want you to try another example. Luis, we'll go with Luis as his name, plays 3 tennis matches. Go ahead and pause the video and make a tree diagram of all his win and loss potential. How many possible win-loss options are there? Okay, go ahead and give it a second. Try and figure this out. Well, hopefully you've unpaused the video now and you took some time. So the question becomes, how do we make the tree diagram for this? Well, there are 3 different games, and each game has a different potential. Win, loss, win, loss, win, loss. Okay? So, how are we going to figure this out? Well, there are different ways we can set this up, but what seems to make sense is he plays a total of 3 tennis matches. Tennis match 1, tennis match 2, and tennis match 3. 1, 2, 3. Now within that, he could win or lose each game. And so what we end up with is a sample space of 6, right? He could win his first 2 games and lose his last one and go 2-1. He could lose his first and win the last 2 and go 2-1. He could lose all of them. He could win all of them. You get the idea. Okay, but that's a tree diagram you could make. All right, let's move on. Let's do another example. There are 5 balls in a bucket. 3 are red, 2 are blue. You were to take 1 ball out, write down its color, and then take out another. Then we want to make a tree diagram of the situation, and then we want to look at some probabilities. Okay? So, how could we set this up? Well, first things first, pause the video and try and make a tree diagram. Once you've paused the video, or once you've made it, unpause the video and check yours with mine. Let's think about the situation here. I am selecting, it might seem confusing because there are 5 balls in the bucket, but don't let that throw you off. I am taking 1 ball out, writing down its color, and then taking out another. So all my tree diagram is going to be, is I'm going to select the first ball. There are 2 options for the color. We could have a red ball or a blue ball. And then after you select the first ball, you again have a second level with 2 options because you're taking out another ball. A red ball or a blue ball. Okay, so this will be my tree diagram. Again, don't get wrapped up in how many balls in the bucket. Your tree diagram is based on how many you are selecting. Okay? So let's go from here. We made our tree diagram. Now we want to come up with some probabilities. What's cool about a tree diagram is it actually makes multiplying probabilities and finding the probability of things very easy. But before we can find the following probabilities, we just need to find the probability of each section. So let's go to our tree diagram. Well, there are 5 balls in the bucket, okay? Now, what it is important to remember is, are we replacing or not? They tell me there are 5 balls in the bucket, 3 are red or 2 are blue. We're taking 1 ball out, then taking out another. This is a form, if you think back to 5.2, dependent probability, right? The first selection will affect your second one. So what are some probabilities here? Well, the chance of me selecting a red ball right out of the bat is 3 out of 5. Okay? There are 3 red balls, 2 blue. Similarly, the blue will be 2 out of 5. Now, what is the probability of the branches below? Well, this probability depends on the first selection. Okay? If I select a red ball and then try and select another, I have a 2 in 4 chance. Okay? I have a 2 in 4 chance because I'm not replacing that first ball. If I don't replace it, now I only have 4 balls in the bucket, and I already took out a red one, and so there's a 2 in 4 chance. The blue, on the other hand, though, here is also going to be a 2 in 4 chance. Again, there were 2 balls initially in the bucket, and if I take a red one out first, it doesn't change the probability of the blue in the numerator, but will change the overall number of balls in the bucket. What happens if I select a blue ball first? Well, then there's a 3 in 4 chance that I select the red ball. Okay? I haven't taken out a red one yet, but there is a 1 in 4 chance that I select the blue ball. Okay? This is because the first ball I took out was blue, so there's only 1 left, 4 total balls. You get the idea. Okay? Well, now that I have the probabilities of each thing happening, now I can do the and probability. Again, I've already accounted for the fact that it's dependent by changing the probabilities in the second half of the tree diagram. So now I can just multiply the probabilities together to find my answer. Okay? In other words, in 5.2 we talked about how do we find an and probability? Multiply the probability of the first event times the second event given the first occurred. So what's the probability for R and R? Well, it's going to be, there's a 3 in 5 chance I select a red ball first, and there's a 2 in 4 chance that I select it second. Multiply those together, and we get a grand total of 6 over 20. Okay, 6 over 20. Again, now that I've given you an example, go ahead and try and fill out the other 3 probabilities. Okay, now that you've paused the video and done that, let's find the others. So the probability of red and blue, well, I'm going to do 3/5 times 2/4, and I'm still going to get 6 out of 20. If I do 2/5 times 3/4, over here in the blue, 2/5 times 3/4, I'm going to get, again, 6 out of 20. And 2/5 times 1/4, I'm going to get 2 out of 20. Why should this answer make sense? Well, if you look, I've covered, there are 4 options that make up my sample space. Red, 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 blue, blue, red, blue, blue. When we talked about this in 5.1, if you add the probabilities of everything in your sample space, it should add up to 1. Do my probabilities sum to be 1? Yes, they do. Okay? The tree diagram is a very useful way for visualizing probabilities and can be really useful in solving problems. Now, what I want you to think about is how would this be different if we didn't, or if we did replace the ball? How would this be different if we did replace the ball? Well, my probabilities in the first part would still stay the same. But what would change is these secondary probabilities. You see, there would then be a 3 in 5 chance still that I chose a red ball. There would be a 2 in 5 that I chose a blue. 3 in 5 and 2 in 5. Again, what you would still find is all the probabilities. If you recalculated the probabilities over here, they will obviously be different. Now they're going to be out of 25, but again, your sample space will still add up to 1. It would just be 25 over 25. So that's tree diagrams. Okay? If you want a verbal summary, they help us visualize all the potential outcomes. We can also use them to display probabilities. So continuing with our problem-solving theme, I want you to think of a dinner party. Pause the video and see if you can figure out if there are 8 seats at a table, how many different ways could we seat 8 people at the table? Okay? Well, hopefully you've paused it and thought about it. Hopefully you came up with a number. I'll give you a hint though, if you came up with 64, you're not quite right. And here's why. Let's logic through this problem together. We have 8 seats at the table. That means there are 8 different options. If we have 8 people, there are 8 different options of people who could sit in seat number 1. 8 different options could sit in seat number 1. Now, someone has to sit there, which means there are only 7 different options for seat number 2. Okay? But if we labeled the people with numbers, you're going to quickly find out that just like when we roll die, the probability of a 5 and a 5, we do 1 in 6 times 1 in 6, get 1 in 36. You would do the same logic here. Okay? If person number 1 sits in that seat, it's different than 2, then 3, then 4, then 5, then 6, then 7, then 8. Okay, there are 8 potential for that first, 7 for the second, 6 for that third seat, 5 for the fourth seat, and so on and so forth. What do we do with all these probabilities? Well, as we've been doing with compound, we would multiply them together. So to figure out that 8 different combinations, or all the different combinations, we would have to multiply 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. When you do that, when we multiply it out, if you do that in a calculator, you get 40,320 different options. 40,000 different ways I could seat 8 people at a table with 8 chairs. Seems huge and impossible, but again, if we think about it, it makes sense. There are 8 different options of seating someone in that first seat. Then there are still 7 for the second, and 6 for the third, and so on and so forth. And when we add all those different options up or multiply all those out, we do get 40,000. Okay? So is there an easier way to do this? Well, what happens when it's not 8? What if we did 17 seats at a dinner party for 17 chairs, or 100? It's going to take you forever in your calculator to do 100 times 99 times 98 times 97, which is why in math and stats we have this thing called a factorial. A factorial is the product of a number and all the numbers below it. We just did 8 factorial when we multiplied 8 times 7 times 6 times 5 times 4. What's the symbol for a factorial? It's the exclamation mark. Simply put, in the example we did above, when we did 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we did 8 factorial. And if you go in your calculator, you'll see it. I believe it's on your formula sheet. Let me double check here. The factorial key, if you press the math button and you tab over to PRB, you're going to see the fourth one down is that exclamation mark. Go ahead and try to hit 8 factorial in your calculator. So type the number 8, press the math button, tab over to PRB, scroll down to the fourth one and hit enter, and you're going to get the exact same number I did. Okay, so that's a factorial. Now, how could we show a factorial on a tree diagram? Well, quite simple. For that first, if we're doing 3 factorial, we know that's 3 times 2 times 1. So we could show it on a tree diagram with 3 different options. For the first, 2 for the second, and 1 for the third. You find out that 3 factorial is 6. And we can see that in the sample space. So back to the earlier point, if you don't believe me for that dinner party of 8 people with 8 seats that it's 40,000 different options, I encourage you to make the tree diagram. Start with 8 potential options for seat 1, then move to 7 for each branch for seat 2, and you're quickly going to figure out why there are 40,000 different options. Okay? Moving on. What happens though if I have a dinner party and I have 8 people coming over, but I only have 5 chairs at the table? Well, how many different options are there to seat these people? 8 people, but only 5 chairs. So 3 are kind of standing around. How does this change things? Well, let's think it through. There are 8 people there, so there are still different 8 potential people who can sit in this first seat. But someone sits down, which means there's only 7 for the second, and 6, and 5, and 4, and then the other 3 people are standing. So you can kind of logic it through and go, okay, well, it's going to be 8 times 7 times 6 times 5 times 4. Well, what happens if we're doing it for a bigger group, though? You showed me the factorial as a shortcut for doing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but what do I do here? Well, this is called a permutation. You see, a permutation is arranging things in a way where order matters. And that's what we've just done there. We've said the certain seating position, it matters who sits in the first seat and the second and the third and the fourth and so on and so forth. So we said that what we would do is 8 times 7 times 6 times 5 times 4. And when we do that in our calculator, we end up with 6,720. The shortcut, though, is using the formula for permutations. What is that formula for permutations? N factorial times n minus r factorial. Now, what are n and r? Well, n is the total number. N is the total number. It's going to be, in this case, n would equal 8. It's the total amount of options we're looking at here. R, on the other hand, is the number we're interested in, or the number we're choosing. So here, we have 8 people, but we only are going to seat 5 of them. So R would be the number we're choosing. Well, let's try the formula. For our dinner party example, it'd be 8 factorial divided by 8 minus 5 factorial. When you do that, we know 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 minus 5 factorial, well, 8 minus 5 is 3, and 3 factorial is just 3 times 2 times 1. But what you notice here is because these are all multiplied together, we're dividing by the same number, so they cancel, and we're left with exactly what we solved for earlier. This is where the permutations formula comes from, okay? We have 8 different people, but we're only choosing to sit 5 of them. And you can see here in action how the formula works. But what's cool with your calculator is there's an even easier way of doing it. You see in their calculator, there's this function called NPR. That's not how you're going to see it, sorry. And it's the permutations formula built in your calculator. So what I want you to do is I want you to hit the number 8, because as this NPR shows, you're going to enter in your number, your total number first, Then I want you to hit the math button, tab over to PRB, and you'll notice it's the second one down is NPR. So then hit the button. And then you enter in your R value, or how many you're choosing. We chose 5. And boom, we get our answer of 6,720. Do I care how you calculate this? I don't. I don't care if you like working it out in hand. I don't care if you want to use n factorial or n minus r factorial. I don't care if you want to use the calculator function. What I need you to know is a permutation is a way of arranging things where order matters. We care who sits in the first seat, in the second seat, in the third seat, in the fourth seat, right? We'll talk about what happens when order doesn't matter here in a second. But first, let's do a problem. Say a board of directors is looking to refill the following positions after the end of their 3-year terms: president, vice president, and treasurer. There are 12 candidates. How many different ways could we fill the position? Well, the first question you're going to learn to ask yourself with these problems is, does order matter? And in this case, yes, order matters. Why does order matter? Because out of the 12 candidates, the one that we select for president, it matters whether they're president, vice president, or treasurer. We want our best person to be the president, our second best to be the vice president, and our third best to be the treasurer. In other words, I'm not just choosing 3 people and it doesn't matter whether they're president, VP, or treasurer. No, order matters here. I do care about it. So what I'm going to do here is I'm going to use the permutations formula. So when we determine that, okay, we want to arrange things or figure out how many different options there are here, and we have identified that order matters because we care about the best person being in the best position, then what we're going to do is we're going to use our permutations formula. N factorial over n minus r factorial. Now in this case, what is our n and what is our r? Well, there are a total of 12 candidates, and we are selecting 3 of them. So we put these numbers in our formula, and we enter it into our calculator. And when we do this, we are going to end up with an answer of 1,320. 1,320. Again, you could have used the formula in blue, or you simply could have used the NPR formula in your calculator. Doesn't matter to me. Either way, you should enter or end up with the answer 1,320. I'd even recommend doing both. Make sure you did it right. Okay? But there are 1,320 different ways that we could fill the position. Well, what happens when order doesn't matter? Well, the formula is very similar. The formula for combinations, aka when order doesn't matter, you could think of rolling 2 dice. Doesn't matter which one's a 1 and which one's a 2 in most games. That would be a situation where order does not matter. The formula is going to be slightly adjusted. Our formula for combinations is n factorial times r over r factorial times n minus r factorial. Almost identical, you just have this additional r factorial in your denominator. So, similarly in our calculator, there's an equal function. If we type in our n value, then we go over to math and we tab over to PRB, you're going to see the NCR formula in your calculator. Again, this does the exact same, very similar to permutations, except it'll run the formula for combinations. Just enter your n and your r values. So what's a practical example? Well, unlike the voting example where we're choosing a treasurer, a vice president, and a president, we want our best to be the president and so on and so forth. It's not the same. If we are selecting 3 people out of 12 to go to the convention, how many different groupings of 3 people could there be? Order doesn't matter here. It doesn't matter if I'm the first chosen or the second chosen or the third chosen. We're all going to the same convention. One of us isn't more important than the other. So in this case, order would not matter. We would use NCR. Again, my N value here is 12. My R value is 3. And so what I'm going to do is I'm going to use my NCR formula. 12 factorial divided by 3 factorial times 12 minus 3 factorial. Or in short, you can do 12C3. Either way, when you do this, you end up with 220 different options. And what I hope you notice is that this number is significantly less, okay? Significantly less than the number of permutations. And this should make sense. Think about rolling dice. If I care what the order is, if I roll a 1 and a 2, that's different than rolling a 2 and a 1. Whereas if order doesn't matter, a 1 and a 2 and a 2 and a 1 are the same thing. They both sum to 3. If you think about the board here, if Jack, Jim, and John all get chosen for the president, vice president role, well, it matters what order they're in. Do we want Jack to be president? Where's Jack going to be the treasurer? What's John going to do? Whereas Jack, Jim, and John, no matter what order they're in, are going to the convention. Typically, combinations will always create less options than permutations, and hopefully that makes sense because the order doesn't matter. Okay? Final question. Final thing to think about. And this one, now that we've learned about permutations and combinations, I want you to try on your own. You're asked to read 4 books out of a list of 10. How many different options could you select? What if you were asked to write a book report on a book that you had not read? How many options are there? What about if you were allowed to use any book, one you had or had not read? Okay? We're asked to read 4 books out of a list of 10. How many different options could we select? Well, let's think it through here. I know the first question that pops into our mind is, does order matter? I'm asked to read 4 books out of a list on 10. There's no indication that my teacher prefers me reading certain books over the others. So here, to answer this question, I would use combinations. If I do there are 10 books, and I'm selecting 4 of them, there would be a total of 210 different combinations of books that I could read. Picking 4 books out of a list of 10 where the order doesn't matter, there are 210 different combinations. What if you were asked to write a book report on a book that you had not read? How many options are there? Well, again, we need to look at our NCR here because, again, the order isn't super important. But what becomes really important is our N value and our R value. Okay? What if you were asked to write a book report on a book that you had not read? How many options were there? Well, there are only 6 books that I did not read because I read 4 of them. I'm choosing 1 to write a book report on. Therefore, to find this answer, how many options are there? I am going to do 6. And I'm going to choose 1. When I do this, I get a grand total of 6. There are 6 different options. And if you think about this logically, if you didn't know permutations and combinations, this should make sense. We read 4 books. There's 6 left. I have to pick one of them to write a book report on. So there's 6 options. Let's talk about the final question. What about if you were allowed to use any book, one you had or had not read? Well, now I have 10 different options because between the books I haven't read and the ones I have, the 6 I haven't, the 4 I have, I'm allowed to use any book, so there are 10 total, and I'm choosing one of them. When you calculate this, there will be 10 options. And again, if we think about this logically, it should make sense. I'm picking out of a list of 10 books, one I get to write a book report on. 10 options. Guys, I hope this introed to you the importance of tree diagrams. It introed factorials and all the different potential combinations. And I hope you see within that the difference between order mattering and order not mattering. You are good now to try the 5-3 work. If you have any questions that aren't making sense in the video, come ready for those on Monday. Again, you don't need to start the 5-3 practice until Monday. So what I would recommend is if you want to look at the problems, go for it, but you don't have to. But really star the things in your notes that aren't making sense so I can help explain them. Have a great day.